Hello everyone, I'm Jiang Kaiwu from Peking University. In this talk, we will present ZGaming, a novel 3D cloud gaming system based on image prediction. This is a joint work by Peking University, Communication University of China, and Tsinghua University. First, why do we care about cloud gaming? In cloud gaming, the heavy computation and the storage are offloaded from the client device to the cloud server. The client only needs to act as a video player. This enables a thin client to run complex 3D games. As a promising way for next generation video games, more and more commercial cloud gaming platforms are emerging. However, one still unsolved problem is interactive latency. It's the time between the user making an action and the corresponding frame being received on the client device. Usually, the latency should be less than 60 milliseconds in order to obtain the same experience as a local game. But in many cases, it's around 120 milliseconds or larger. So there is a gap between the current performance and the user satisfaction. To reduce the interactive latency, we can optimize the network to reduce RTT. But ZGaming follows another approach. Instead of waiting for receiving the real frame, ZGaming responds to user action with predicted frames. In this way, users can be responded immediately and don't experience any interactive latency, which means zero latency. The most widely used prediction method is deep image-based rendering, DIBR, which can project the contents from input frame to a new viewpoint. So in cloud gaming, once the user takes an action, we can use DIBR to predict the frame under the moved viewpoint. To evaluate the potential gain of DIBR, we add it to a traditional cloud gaming system. We use PSNR to measure the visual quality. The higher the value, the better the user experience. Our result indicates DIBR can reduce the latency to zero, but leads to a huge drop in visual quality. This is because DIBR introduces many errors when predicting images. So in ZGaming, the key is to improve the performance of image prediction. To do this, we face three challenges. First, how to reduce the Hall artifacts. As shown in the figure, there are many missing pixels on the predicted image. This is because the sense content in those areas was not sampled in the input frames. We refer to the missing pixel as Hall artifacts. To reduce the holes, we need to enrich the sense contents for DIBR. But where can we get more sense contents? Our answer is the history frames. To analyze how much the history frame can reduce the holes, we evaluate the performance of DIBR with a single frame and DIBR with all history frames. As shown in the figure, the result indicates that adding the history frame can significantly increase the pixel coverage of DIBR. In this way, the Hall artifacts from uncovered pixels can be reduced. However, the end device needs huge storage to store the history frames because even one single history frame will occupy 12 megabytes. To reduce storage, we propose two methods. First, we split each history frame into blocks and catch only one block for the same contents. Second, for each catched block, we compute its utility value and replace the low-value blocks in real time. The second challenge is DIBR doesn't work for the dynamic objects. As shown in the figure, there are many mismatches between the predicted image and the ground truth image. This is because DIBR predicts by projecting contents recorded in the input frame. For static objects, DIBR works well. But for the dynamic objects, such as the in-game character, they are always in motion. Their real positions, poses, and appearance are always changing. So the content stored in the input frame is already outdated, causing prediction errors. we observe that the motion pattern of dynamic objects can be learned from frame sequences. So an LSTM model is proposed to deal with dynamic objects. The model architecture is shown in the figure. By inputting the previous 5 frames, the model can directly predict the next 5 frames in an end-to-end manner. The third charge is bitrate selection. When selecting the bitrate, existing algorithms tend to increase in the bitrate, which limits the prediction performance. To prove this, we show the prediction performance on the different video quality and the interactive latency on the left. On the one hand, increasing the bitrate can reduce the image distortion caused by encoding, so that the video quality will be higher, leading to a better prediction performance. On the other hand, increasing the bitrate potentially leads to an increase in latency, resulting in a longer prediction period, which in turn reduces the prediction performance. To address this, we take 3 steps. First, based on the current bandwidth, network delay, and the package loss rate, we estimate the interactive latency at a given bitrate. Second, based on the latest prediction performance, the estimate latency, and the corresponding video quality at the given bitrate, we estimate the prediction performance at the given bitrate. Finally, the bitrate that maximizes the estimated prediction performance will be selected. Next is our evaluation. The evaluation is based on real-world recordings of a popular 3D game. As for the network settings, we collect network traces from a real-world popular commercial cloud gaming platform. We compare ZGaming with 2 existing cloud gaming systems. GameAnywhere is a well-known traditional cloud gaming system without prediction. DRBR is a cloud gaming system that uses DRBR to predict images. This figure shows the CDF of video quality while maintaining zero latency. It indicates that ZGaming can significantly improve the video quality experienced by users. For example, ZGaming's video quality is above 33 dB in 40% of cases, compared with only 9.5% for DRBR and 4% for GameAnywhere. On the other hand, ZGaming can significantly reduce the probability of user experiencing low video quality. For example, ZGaming has only 3% of cases where the video quality is below 25 dB, while DRBR has 40.5% and GameAnywhere has 50.5%. To sum up, in cloud gaming, interactive latency is one of the most important factors in users' experience. Our vision is using predictive frames to respond to user actions immediately, enabling a zero-latency cloud gaming experience. The key challenge we face is how to prove the quality of predicted images. For this, we mainly propose 3 methods. First, a quality-driven broad cache to reduce the whole artifacts. Second, a LSTM model to predict dynamic objects. Third, adaptive bitrate algorithm to optimize the performance of image prediction. The evaluation results show that ZGaming can significantly higher video quality experienced by user while maintaining zero latency. Thank you.